There we go. We're going to go to the tail end of chapter 2 and finish up naming acid. But since this is a review, maybe what we should do is run through the naming rules. Okay. Let's try a different color. So the starting position for naming is binary compound. Is you have a cation and an anion. In other words, a positive and a negative together. So the type 1 are between metal, non-metal, and the metals are fixed charge. I should say single fixed charge. That is, there's only one possibility for the charge on the metal. And this would be the cation, of course. The non-metal would be the anion. And they're always written cation first, anion second. Okay? So where do we find on the periodic table the fixed charge metals? The alkali metals, they're always +1. Alkaline earths, always +2. And aluminum, gallium, and I think indium. Aluminum definitely is always 3+. So it's 1+, 2+, 3+. When you combine those with an anion, of course, noble gases don't count because they don't play well with anybody. But the halogens are going to be -1 in this situation. The chalcogens, oxygen group, are going to be -2. And the nitrogens, or the nitrogen group, are going to be -3. When you get over here, all bets are off. You can have these in a metal, non-metal situation, but they're not as common. Okay, so how do we name them? Well, you just use the name. Let's do it with an example. All right. Let's say we want this one right here. Sodium combined with chlorine. Right? So if sodium's always +1, chlorine's always -1, 1 and 1. That's it. Charge is balanced. Right? That's what you want. You want a neutral situation. Unless there's a charge on the group, it's always neutral. So this one has to balance that one. Okay? So the cation you just name as the element name. And the anion you change the ending to IDE. Sodium chloride. Okay. Table salt. Let's try another. What if we wanted to form a compound with chlorine, but instead of using sodium, we use calcium? Calcium comes from the alkaline earths. So what charge is it? +2. Right? You can write these in there just, you don't have to write them when you actually write the compound. But if we're budgeting charges, then it's helpful sometimes just to pencil them in. Right? So how do we neutralize that one? Because this one's 2+ and that one's only 1-. So you got an extra plus floating around, right? Can't do that. So you with 2 chlorines. That's 2 minuses against the 2 pluses, and we're neutral. Okay. Remember when I showed you the 4 positions around the element symbol, right? This position is always reserved for, how many of them are there? Right. This position is always reserved for charge. Right. And this position is for atomic number, and this one's for mass number. We don't need either one of those for these, because the symbol tells us what the atomic number should be. Right? So what's the atomic number for calcium? If we were writing in, but we don't have to. 20. Right? 20 protons. Now the mass number is a little different because of isotopes. Right? But you can take an educated guess. What are most of the isotope mass numbers going to be? Probably 40. Right? That's going to be the majority of the calcium isotopes. It's going to be 40 because this number is so close to 40. And since it's larger than 40 on average, the next isotope is going to be greater than 40, probably 41. We don't know that unless we're told, but that's a good guess. Sodium, probably most of the sodiums are going to be 23. And then the other isotope might be 22, which would decrease the average below 23. But for naming purposes and writing the compounds, you don't have to put those in. You just need this one. And if there's a charge, if we're writing an ion, then you write the charge in. Or if you're budgeting your charges, you can pencil them in. Right? So you keep track of your charges. But overall, we're neutral. Okay, so this one would be calcium. Chloride. We don't have to say how many there are because there can only be one set of charges. And this is the only name that will give you that compound. See, the naming conventions are designed so they're not ambiguous. Unambiguity is the goal. And simplicity. So for the type 1 compounds, we don't have to say either what the charge is here or how many of these there are. Okay, any questions so far? All right, type 2. Okay, type 2s are also metal, non-metal. But for these, the metal has possible multiple charges. Okay? That's the only difference between the two. So you still have the convention of cation, anion. And then where do the cations come from? Well, any other metal besides the one we showed you, right? Most of them are likely to come from transition metals, but they could come from in here as well. But you can have multiple charges in here and here. And if you look on for the copy of the periodic table I handed out, yeah, it does have charges. So if you look in the upper right-hand corner of each one of those boxes with the elements on the periodic table I handed out, you'll see for the transition metals especially, there are multiple charges possible. Whereas with these two and these, you should see only one charge. But for the others, the transition metals and these metals in here, you should see multiple charges possible. So that being the case, we have to specify what the charge is in the name. Right? We do that with a Roman numeral. So let's take an example. How about this one? Let's say I want to combine iron and chlorine. That doesn't tell me anything because iron could be more than one charge. You have to say what the charge is. So let's say the charge is 3+. Chlorine is still 1-, right? So you need 3 chlorines, right? 3 times the -1 is -3. Balances 3+. Okay. Now we want to name it. We just say that the element. I'm going to leave a space here. Chloride. And then what goes in here? Roman numeral 3. Okay. That's unambiguous. You can take this name and write that compound. Or you can take this compound and write that name. There's no other possibilities. If you do it correctly, follow the rules, you won't make a mistake. Let's try a different one. How about this one? What's that? Lead. Let's say our lead is, let's say it's a 2+ charge. Lead is usually either 2+ or 4+. And let's combine it with something else besides chlorine. How about oxygen? What's the charge on oxygen? 2-. That's it. They balance. 2+, 2-. You only need one of each. So let's name it. Lead oxide. With the charge on the lead. Right? We didn't put that charge in there. It could have been this one. Because lead would have been 4+. And in that case, you would write lead 4 oxide. This one.
So, question, how do we know if it's 2 or 4?
We tell you.
Okay, all right, that's all.
Yeah.
That's all I was wondering.
It either has to be given to you, in this case, or if the name,
Compound.
if you want to write the compound from the name will give you the charge.
Okay.
Yep.
I was curious about how to figure out if it's 4 or 2.
Right.
That's all I need to be telling us.
Yeah. It makes you wonder, under what circumstances am I going to have to reason this out for myself? With naming convention, you're given that stuff. Okay. Type 1, type 2, type 3. So type 3 is a completely different animal. Non-metal, non-metal. Okay? So where non-metal and non-metal are concerned, you don't actually have charges. We only borrow the naming convention from type 1, type 2, or type 3, to write type 3 compounds. But, and in this case, this is the true situation, no charges. Because when you get 2 nonmetals together, the only way they combine is by covalent bonding. That is, they share electrons. Nobody gives up their electrons completely, so you don't have ions. Okay? So for type 3 compounds, non-metal, non-metal, no charges, we still use the cation-anion convention. But you have to be given how many of what element there are. So let's take a familiar one. Okay? You write this one as if this were the cation, so that one is just write the element. And And then oxygen becomes oxide. But you have to say, exactly. You have to say how many. Now, for the first one, you don't say mono. If it were in the second position, you would say mono. But for convention and for aesthetics, we don't say mono in the first one. We assume that if the name is there, there's got to be at least one. So if you say carbon, there's one. Did I see a hand go up? Just a stretch. So if we were to write this one, this is supposed to be the one that's responsible for global warming. We all know that's false. But this one is the poisonous gas. And taking aesthetics into account, we don't say monoxide. We just keep one of the O's, monoxide. It just flows better. Chemists are not completely unmindful of this aesthetics. Okay, so let's try another. Well, so in order to use this convention, you've got to know what your Greek prefixes are for numbers, right? So mono, di, tri, tetra, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10.
So if we can say C, okay, say carbon,
Mhm.
and they have 2 between C and O. We would write it dicarbon oxide.
Oh, okay. Let's use a real compound. Okay.
I'm just
Right, I get your drift, but well, you could have something like that. But let's use something else. How about this one? This is a real compound. Exactly. That's what we call the trivial name, nitrous oxide. It's an older convention. Nowadays, the IUPAC name, I told you what IUPAC was, International Union of Pure and Applied Chemists. Okay. The IUPAC name says it's di-nitrogen monoxide. Okay. Nitrous oxide refers to what's the formal charge on N. We haven't got to that convention yet, calculating formal charges. But N2O is nitrous oxide, dinitrogen monoxide, laughing gas. Okay, so those are the general conventions, and then we come to talking about acids. Let me get my notes. Keep me from drifting. Okay. First of all, how do we recognize an acid? The hydrogen, right? There's always at least one hydrogen listed first in the compound. So this would be an example. This would be another example. This would be another one. This would be another one. Even this one. See, I always have to think about this one. The reason I put that one in there is because we've got hydrogens here and here. So what happens, first of all, well, hold that thought. I'll get to that. I don't want to complicate things too much. We're talking about nomenclature now, so let's deal with nomenclature.
Oh, that's how you know it's acid. Hydrogen first. Is that right?
Yes, hydrogen first is the clue for an acid. So, if this were a gas, we would call it hydrogen chloride. Okay, that's a valid name. They only become acids when they're dissolved in water. Okay? So if we dissolve this in water, more space. If we dissolve this one in water, so it would be aqueous. Okay? Then we would call it, we would look for oxygen. Okay? If there's no oxygen in the molecule, then you don't start the name with hydro. You do start the name with hydro if there's no oxygen. Okay? So this would be started as hydro. And then you look at the element that it's combined with and change the ending to ic. Hydrochloric acid. Okay. So the key there is, does it have oxygen or doesn't it have oxygen? If there's no oxygen in it, then we start with hydro. If there's oxygen in it, you don't start with hydro. You just go to this part of the name, and this, and that's why in the extra credit, the 50 ways to name your compound, there's a page in there with polyatomic ions listed. Okay, we didn't talk about polyatomics. Okay, polyatomics are groups of elements, atoms if you will, that behave as a single unit. Okay, so this behaves as a single unit bound to that one. This one is a single, that one's a single, this one's a single. Okay, those polyatomic ions have names. In this case, this would be a plus charge because all acidic hydrogens are protons, so that would be a plus charge, right? Look at hydrogen. It only has one proton in its nucleus, right? So if it's neutral, it has one electron. If it loses that electron, what is it? Well, it's a hydrogen ion, but it's also a proton, right? That's all that's left. It's just a proton. So each one of these can be viewed as 2 protons, 3 protons, 1 proton. Combined with, in this case, would have to be a negative charge on that group, right, to balance. So that group is there. This has 2 of them, right? So this has to be a 2 minus. That one has 3. This is a 3 minus. This is only 1 plus, so that's a 1 minus on that group. And if you look up in that chart, the polyatomic ions, you can find that this one is called nitrate. This one is called sulfate. This one is called phosphate. And this one is called acetate. They all have oxygen in them, so we don't start their names with hydro. We just look to the anion part, and ATEs become X, H6. So this is nitric acid. That's it. sulfate, 8 becomes X. Well, aesthetics again. Instead of sulfic, we say sulfuric. Phosphate becomes phosphoric. And acetate becomes acetic. You know what acetic acid is? If it's 5% solution, it's vinegar. Okay. So, the first rule in naming acid is, does it have oxygen? Right? If it doesn't have oxygen, you start with hydro. And then you change this to, well, in this case, it has to be aqueous. You change it to hydrochloric. Ick. If it's not in solution, then you use that convention. Okay. If it's aqueous. So when you answer these extra credit questions, some of them might have left off the this parenthesis. If it doesn't say what it is, then technically you could name it either way, and I'll accept it. But what I'm really looking for is the acid name. Okay. What's another example? Let's say, how about this one? Okay. Now, how do you know you're dealing with a polyatomic ion in a compound? Well, the best way is to memorize it. Or suspect and then look them up in your chart. Because on the test, you will have one of those polyatomic charts and useful information. Okay, so you don't have to memorize all. But you'd be wise to learn where to find them all, okay, in the chart. But how do you suspect? Then if you're going to use the chart, you need to suspect that there are polyatomics there. Well, the best way to suspect is there are at least 3 elements in the compound, and one of them is oxygen. Now, it's not always the case like this one. Right? That one's got 3 in it, all right, so that's half suspect. But this is the cyanide ion. Right? So if this were a gas, how would we name it?
It'd be hydro.
Okay, let's name it as a gas first. Right, use that convention. So you put the cation, hydrogen, cyanide. With polyatomics, you don't have to change the name, except when you're naming it like this. If you're naming it like this convention, then the name of the polyatomic is given in the chart and you keep it. So that's the cyanide ion, you just write it as cyanide. Okay, now we're going to go aqueous. So we're dissolving hydrogen cyanide in water. There's no oxygen, right? So how do we start the name? Right? I try not to give trick questions. They're pretty straightforward. Hydro. Now, we're going to change the ending to suit the convention. If it's the cyanide ion, we change ide to ic. Like chloride to chloric, cyanide to cyanic. Acid. Notice we don't put acid here, because that's not in solution. In order for that hydrogen to dissociate from the compound and be available in solution to express acidity, it needs to be acidic. on chapter 14 and 15. Did we get to those chapters? I don't think so. That's the second semester. We go into a lot more detail on acid. And we learn how to do equilibrium equation, how to find out what the concentration is of the hydrogen in solution. But for now, when you put it in solution, these hydrogens dissociate. Right? The hydrogen ion concentration tells you how acidic the solution is. Right? One expression for that is, you've probably seen this one before, pH. Right? That's an expression of hydrogen ion concentration. And it's got to be an aqueous solution in order for those hydrogens to dissociate.
I was going to ask you, what's the strongest acid of it?
The strongest one? Oh. Well, okay. Those are relative terms. This is a strong acid. That's a strong acid. That's a strong acid. Those three are generally considered strong acids. But they're only strong for the first hydrogen. Since this has only got one, this gives up that one. Completely dissociates. All of those hydrogens go into solution. Okay. So same with nitric acid. Sulfuric acid, only the first hydrogen goes into solution. After you remove the first hydrogen, it becomes more difficult to remove the second one. Because what do you have? I ran out of room over there. You do this one, I'm giving you a lesson from next semester. So you have this one plus what's left over. Right? If you take that positive away, you got a negative, right? Okay. So now, if you try to remove another positive from that negative group, it's more difficult, isn't it? Because of electrostatic attraction. Right? So this is a strong one. That's a weak one. Okay, but it's still considered a strong acid because of that first proton. And the corrosivity of an acid also depends on its concentration. Right? You can have hydrochloric acid at such a low concentration, you might as well drink it as water. Or in your stomach, concentration gives you a pH of between 1 and 2. So that's fairly concentrated. You know, it's enough to start breaking down your food. Okay. So let's see if I missed anything. All right. They don't talk about bases here. Bases you can use either one of these conventions. So if we say this one, you look in your chart and find that OH is a polyatomic ion. It's called hydroxyl. So this would be sodium. Well, and then the hydroxyl ion, hydroxide ion actually. So this is hydroxide. And most bases have the hydroxide on the end. So you just plug in a different metal. Now, of course, if you have this one, that tells me, since this is a -1, and remember, when you have more than one polyatomic ion, it acts like a single unit. So you have to put a parenthesis around it if you need more than one of them. Okay. So we needed 3 of these. That's because that charge is 3 plus. 3 times 1 minus 3 minus 3 plus. So in this case, we have iron 3 hydroxide. That's a weak base, by the way. It doesn't dissociate very much in water. Strong bases, sodium hydroxide is a strong base. Lithium hydroxide is a strong base. Potassium, rubidium, cesium, all of these form strong bases. In other words, when you put them in water, they completely dissociate. That's what hydroxide is. The concentration of your compound is equal to the concentration of hydroxide in aqueous solution. These are considered strong bases, but they don't dissociate as well. So that's a technicality I'm not going to hold you to right now. We'll deal with that second semester. Okay, let's see if I missed anything. Okay. Let's look at, how we doing? Okay, almost 9 o'clock. I'm going to erase this so I'll have room to talk a little bit more about acids. If you look at that list of polyatomic ions, some of them, there's a method. Down one side, down the left-hand side, these are sorted alphabetically by name. Down the right-hand side, they're sorted by formula. So the grouping is more logical on the right. On the left, it might be easier to find. But they're equivalent lists, left and right. You'll notice that, let's see, when you combine chlorine and oxygen together, it can combine in different ratios with oxygen, which means you have different names for the polyatomic ion. But there's a logic to it. You can have, and I start with this one, with a 1- charge. So if you find that one, it's about a third of the way down on the right-hand column. That's called chlorate. Okay? So we start with the 8s. Now, what if we take away an oxygen? We still have the 1- charge, and you can prove that there. Take away 1. What is it called? Right. Change the name to chlorite. Okay? We can take away 1 more oxygen and still have 1 left, and that's as far as you can go. This direction. But we don't have any more simple endings, right? So we have to improvise. We use hypochlorite. So 8 is less than 8, but hypochlorite is even less than 8. Like hypo underneath, hypodermic, under the skin. So hypochlorite, that one. We can go 1 this direction, add an oxygen. And for that one, we need a different prefix for this one. So we went down for this one, we go up for that one. This one is perchlorate. So that represents to me a family of polyatomic ions between chlorine and oxygen. Right? You can do that with bromine as well. Just replace these chlorines with bromine. And replace this, bromite, hypobromite, bromite, bromate, perbromate. Right? So once you've got this method down, you can substitute bromine in there. You can substitute iodine in there as well. So this would be hypoiodite, so forth. But I always start with chlorate, or the 8. It's always 3 oxygens with the halogen for those 3 families. That. Fluorine is a special case. Right, so that's why I don't have fluorine, in case you were wondering. Okay. So if we're going to make acids out of these, You just add a hydrogen on the front, one proton balances the negative, right? So each one only has one proton. So if we add a proton on the front, and we have an oxygen, so we don't start with hydro, we just say, change that to the H's become X. So this would be perchloric acid. This would be chloric acid. The H's become X, the I's become us. This becomes chlorus acid. Okay. And this becomes hypochlorous acid. Okay? Trying to make a logical progression out of this so there's less memorization.
So how did you get the us instead of it?
Convention. I's become us.
Okay.
H's become X.
Oh.
Okay. There's nothing magic about it. We just, scientists just agree that's what we're going to call it. Okay. So, perchloric acid. You're talking about strong acid? That is extremely strong acid. In fact, it's not just a strong acid, it's a strong oxidizing agent too. In fact, I used to use it in the laboratory to oxidize, disintegrate plant material. So it would leave the ash behind, because I was only interested in the mineral content at that time. So all the organic matter I wanted to get rid of, we used perchloric acid. But we couldn't use perchloric acid on our plant material and then heat it up, because it needs to be heated to be active enough to do that job. To do that, there's a chance of explosion because the reaction is so violent. So the way around that was we take nitric acid, which is also an oxidizing agent, but it's not as strong. And we do a pre-digestion. Take our plant material, add nitric acid into our tall beakers, put a cover on them, and let them sit overnight in the accumulator. Then the next morning, we come in and put our perchloric acid on, heat it up. We're good to go. Guaranteed explosion. Let's see. Take a beaker, put a nice generous pat of butter in it, and cover it with perchloric acid. Stick it under the hood on your hot plate. Turn it on high, pull the sash down, and evacuate the building, because it will blow. So there are dangers to using these things, but there are ways around it. On the other end, you can form other compounds with these polyatomic ions, right? So this one, for example, is that. So if we name it by our convention, that's sodium hypochlorite, right? Sodium hypochlorite. 6% sodium hypochlorite is chlorine bleach. Does anybody in here read bottles? No? You're walking through the store, or you get them home. You want to know what's in them? Oh yeah, I read labels all the time. That's where you find this stuff out. Read the labels, right? Because the labels are there by convention. The government says you have to put this information on there. It has to be there by law. The only way they get around that is if they can say this is proprietary, blah, 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 and then they generalize the name. And then you have to go digging. Like you might even have to look up the patent to find out what it is. But it's there, it's out there somewhere. That's how their competitors find out, you know, and they're just waiting. As soon as that patent runs out, we jump on it. And we sell your product at half the price or only 30%, and we steal your market. As long as they got the patent, they don't have to tell you what's in it. But there are some things that you do. You have to say exactly what's in there. And chlorine bleach is one of them. For the longest time, 5.25% was chlorine bleach. But now they have, let's see, what do they call it? The ultra bleaches, they're 6%. And then, of course, they put a thickening agent in to keep it splattering. Right. And that thickening agent has to be resistant to hydrolysis under basic conditions. Right? Otherwise, you put it in there and it just eats it up. So the polymer they put in there has to be resistant to basic hydrolysis. And it also has to be soluble in water, which most of them are, because they got to wash away from your clothes. You don't want to leave that stuff on your clothes, on your whites. Make sure it's just your whites. Non-chlorine bleach is a different story. They're not as powerful as a bleaching agent as this, but they do bleach some things. Okay, I digress again. So that's how you name acids. And there are several acids in your 50 ways to name your compound. Now, if you guys, after seeing some of this stuff, if you say, maybe I named that one wrong, you can retrieve it, take it with you, give it back to me later, if you have that uneasy feeling, okay? Okay, so that's how you name acids. So we can go to a general review now. Unless you have questions about this. Next week is Labor Day. Right? We get that day off. So that gives you an extra week to master this stuff before the exam. Because the Monday we come back after Labor Day is the exam day. 1 and 2. Yeah. Let's see that. Now, if you ever encounter some older literature, acetic acid might be written a little differently. You might see it that way. The same formula, but it's written differently, and it gives you a little bit more information as to the structure of the molecule. Here's your acidic hydrogen. It's bound to this carboxylic acid group. So we'll have this one with our hydrogens, right? 3 hydrogens over here on this group. That's called a methyl group. And it's bound to another carbon. And on that carbon, you have a carbonyl and a hydroxyl group. So this one, that's the one that dissociates. And this way of writing it gives you more information as to the structure of the molecule. And it also explains that these 3 hydrogens are bound tightly. They're covalently bound to that carbon. They do not dissociate. That's why they're written separately here. Okay. But we'll try to stick to this convention because that's what's in the book. But I may just give fair warning, I may lapse because that's the way I learned it originally, and it makes more sense. So if I happen to lapse into that, then forgive me, correct me, I'll rewrite it this way. Okay. Now we can go back to chapter 10 and do sort of a review. Let me see. Did anybody bother to look at the review document that I had on Blackboard? Right, this is a copy of it. Actually, this is the key. I told you about that, didn't I? In Blackboard, under each one of the exams, there's a review document that I used to use instead of homework, but I never graded it because I didn't have time. So that's why I'm using homework now, because Cengage will grade it for me.
Someone told me that they used to do the study data
Yeah,
and stuff.
but it's still there, you know. And it also shows you the format that I use on the exam. It won't have this many questions on it, of course. I mean, it'd take you 3 or 4 hours to finish this one. And we don't have that much time. But it also gives you these last pages, the useful information. Yeah?
So basically, the review guide is what we need to talk about.
It would be good to look over it, yeah. But I was pointing out that if you see on the review document, you see useful information at the end, all of that will be on the exam. I don't hand them all out in class now because I don't give you the review document itself. If I were using that method, then you'd each get a copy of this without the answers. And if you wanted the answers, you just go to Blackboard, find the key. You'd also find how I did it, like the handwritten solution to the problems. So, I'm going to skip stuff that's just pure memory, like you know, the difference between a law and a theory, you know, and the various laws, like the law of definite proportions, the law of multiple proportions. Those two usually get confused by students, so you might want to bone up on that one. But we'll look at problem solutions. How about we start with things like metric prefixes? Okay? Am I comfortable with metric prefixes?
Is this one chapter?
Yeah, we're in chapter 1 now. Yeah, I've reverted.
Just making sure I'm following you in the book.
Okay. So let's say we have these prefixes. Oops. E-N-T-I. And maybe this one. Okay. Let's put them in order from smallest to largest. Let's make it easy first. So which is the smallest one? If you prefix a number with one of these, which one makes the unit smallest? Nano. This is the first one. This is the smallest one. Which one is the largest one? I'm sorry? Right. Kilo. So this is the largest one. It'll be number 4. Then all we have to do is say, what order do these two go in? Which one's smaller of the two? The bottom one. Okay, so that's 2, and this is 3. Okay. So from smallest to largest, nano, milli, centi, kilo. Okay. So what do these mean? All right. If we put this in front of let's say put it in front of a meter. So a nanometer means what to the size of the unit of a meter? 10 to the what? -9. It's a billionth of. We don't have 10 to the -6 up here. What would that be?
Micro.
Uh-huh. That's not in the list, but that would be 10 to the -6. Okay. So -9, -6. Which one's -30? Is it up here? Uh-huh. Let's see. This one's -2. Uh-huh. How about this one? Is that right? Kilo means 1,000 times. What would be 10 to the 6? Mega, right. Now, what are the, what would be the abbreviation of each one? So this one would be just a little n preceding. Let's do meters. So this would be nanometers. This would be kilometers. This would be centimeters. This would be millimeters. How about this one? Right, it's that funny Greek letter. The Greek letter mu. And this one would be, right. So that we don't confuse it with this n. Okay? There it is. The blue doesn't erase very well, does it? Okay. Let's see. How about this one? 0.3980 meters. Convert it to millimeters. So this is a problem in dimensional analysis. How do you get from meters to millimeters? Well, you could do it the quick way. You say millimeters, as the units get smaller, the number gets bigger. Right? That's a good rule to go by. So the number of millimeters from these meters would be much bigger than that number by 1,000 times. So if we did that, we'd move it 3 to the right. (398 millimeters). Right. That's the quick way. But if we have an exercise in dimensional analysis, this is the way you prove it. You need a conversion factor that will cancel meters and leave you with millimeters, right? So, how many millimeters are in a meter? 1,000 millimeters in a meter. Right? If you got time, you can take a meter stick and just count those little tiny marks. Get 1,000. Okay.
I'll be extremely honest. When I was doing the homework,
Say again?
when I was doing the homework and stuff,
Uh-huh.
I went back and read a little bit of the chapters, and I took pictures of the ones I got wrong, stuff and studied them, had it
Okay.
flip and show you.
Yeah.
But this right here is pro.
Okay, so the homework doesn't explain it this way.
It does. It shows you a picture, explains how he did it.
Okay.
But I was like sitting there, something I had to go back and look.
Okay. Lesson in learning psychology. The more ways learning enters the brain from different angles, the better you retain. So hearing, seeing, you say what it is, write it down. Those are 4 different ways. If you do those over and over and over again, besides getting bored, you learn it. Okay, so this is the dimensional analysis way, and this is 1,000 times that does this. That answer. It cancels meters and leaves millimeters. Remember, you can cancel units just as easily as numbers. So we divide meters into meters and get 1. That leaves us with millimeters. There's your answer. Okay. We could talk about accuracy and precision. try this one. Suppose you're given, you measure the mass of some object, and you do it 3 different times. And the first time you did it, let's say it's trial, sometimes we say rep, or replicate, right? So each trial, let's say we do it 3 times, and we get a value for a mass of okay, this one this is an expression of spread. This is our confidence interval. We're confident that the value is between what here? 1.202 and 1.200. Add 1, subtract 1 at that position. And this one. What's the first thing you note about this? With this confidence interval, if we say, what's the middle number? Okay. The average number, how about that? 1.201, right? That's the average. And we designate that with an X bar. That's the since these are all the same, that's good. We don't have to deal with that. So it's got the same spread here. So the average, the spread puts it between 0, 0, and 0, 2. So are the values here? Yep, that one's there, that one's there. So what can we say about the precision of this value? Right, it's small, it's compact. So it is precise. Now let's see, did I give you enough information? No, I didn't give you enough information yet to say, is it accurate, right? We need an accepted value to determine accuracy, right? Precision, yeah, we can do that with just the numbers. Right. What is the expected value or the accepted value for this mass? Let's say you're testing your balance, and you put a 1 gram mass on the balance, and you get these 3 measurements. Is that accurate? No. Way, way off. Not accurate. Those measurements, all 3 of them, are way off base. Right? So this set of data is precise, yeah, but it's not accurate. Let's see. This one. Okay. Let's say you're making a measurement. And we're trying to determine who's responsible for the bad numbers. Okay. So who can we blame it on? Or what can we blame it on for the measurement? Measurement uncertainty, we'll call it that. What factors can we blame it on? We can blame it on the technician, definitely. Who's making the measurement, right? Okay. Let's say the technician is defensive, right? And then we keep their job. So what are they going to blame it on? Well, maybe other technicians that are making similar measurements. Maybe they came in and swapped out a paper on me. That used to happen, especially in organic chemistry labs. That's why all the drawers are locked. You're given your glassware at the beginning, stick it in there. Anything that you produce in the lab, stick it in there, safekeeping. Because there's some, not many, but some unscrupulous students that will tamper with your work, just to blow the curve, they say. All right, so the technicians, their abilities are one thing, but if you can't blame it on somebody else, what do you blame it on?
What?
The instruments, right? Instruments. Okay. Now we could think of a third one, you know, that might come into play. Environment. Right. Let's say the Earth passes too close to a black hole. That screws up your measurement. But these are probably the two that you have some control over. You can say, you can actually determine how competent the technician is. You just give them a standard sample and have them run multiple analyses on it, see how close did he get to the answer, or what their spread is, precision. You can do the same thing with instruments, right? Environment is usually in a laboratory situation, the environment is very well controlled. Temperature, humidity, those types of things. If you have an analytical balance that is that reads out to 6 decimal places of a gram, that's pretty good. But it's susceptible to vibration, right? So what do? Well, first of all, you probably put it in a special room where you can control drafts, and then you have the pan that you set your sample on is enclosed. The doors on the side, so you can close those and let it settle down. But you also need to protect it from vibration. So one thing you do is just get a big slab of marble, right? Lots of inertia. Plus, you put that slab of marble on rubber feet, right? So it isolates it. And then you set your balance on top of that marble, and you're good to go. I used to have one of those balances. And it wasn't easy to measure out small amounts like that, but the instrument that it was measuring for required it. Right? So you just had to do it. But that's how we did it. Put it on a slab of marble with rubber feet. You could make multiple measurements, take your standard gram or tenth of a gram or whatever it was, and you could repeat those over and over again. Okay, we're good to go. So environment can usually be controlled. So these are the two main ones. The ability of the technician and the instrumentation will determine the level of uncertainty of your measurements. Okay. I better get through this chapter pretty quick. How about scientific notation? Let's say we have, how about this one? That number right there. We want to express that in scientific notation. So what's the first rule? A coefficient has to be between 1 and 10. Right? So our coefficient, we have to move the decimal over here so we get 1.65.
Times 10 to the third power.
1, 2, 3, 4, 5. Third power would only bring it here. Now, exponent, did I say exponential or scientific? Scientific, good. Scientific is a subset of exponential. So we move the decimal, the understood decimal, here, 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 here. That gives us 5 there, because we move to the left. This is the positive side, that's the negative side. If we move the decimal that way, this number goes negative. Now, why didn't we include those zeros?
It's going to be that 10 right there.
Hmm?
It's going to be with the.
Why didn't I put 3 zeros out here? they're not significant, right? There's no explicit decimal place right there. That means zeros to the right with no decimal are not significant. Okay? And if you know that rule and you write your scientific notation, then you say, there's only 3 significant figures in that number. So when we rewrite this one as a standard notation, we move 5 places to the right. So we go 1, 2, 3, 4, 5. But we leave the decimal out because we know that there are no significant zeros. Okay? Let's see. How about this one? Let's write that one. So we need a coefficient between 1 and 10. Right? 1, 2, 3, 4, 5. Minus. Because we're moving in the negative direction. Now, this one is easy to say why the zeros are. Because putting zeros in front of that makes no sense, right? So that one's easier to deal with. But when you rewrite it, you got to move back this direction. Right? We just put as many as we need out here. So if we're starting here, we go 5. 1, 2, 3, 4, 5. And then we can erase these 2 because we don't need them. There we go. So we rewrote our scientific notation as standard. Now, if your calculator is set up for decimal places, not scientific notation, but just pure standard notation, you've only got it set to show you 4 decimal places. That's all you're going to see. Okay. So it's probably a good idea to set up your calculator for scientific notation and give yourself 4 or 5 places for your coefficient. Then it'll give you your answer in scientific notation. You can still put the number in like that as entry in your calculator, but then your answer will come out like that so you can actually see the answer. Okay? Speaking from personal experience. Okay. Let's see. What's next? Combining numbers. Got that? Let's take a complex one so we can get through this before lunch. How about this one? Let's say we have 3.478 times 1.164 divided by 2 and then we're subtracting 0.19. Okay, what would be the answer for that? Well, notice there are no parentheses there. It's not telling you the order, so we have to resort to what? Okay, no parentheses, no exponents, so we multiply then divide. So we multiply these 2 together and then divide by that one. Well, since multiply and divide use the same set of significant figure rules, we can do it all at once. So we can do multiply these 2, divide by that one, and get an answer. So let's see, 3.478 and times 1.164, and then divide by 2. Okay, so that gives me 2.02420 on my calculator. But before we can use it, use the add subtract rule, we have to round this one. Right? You can't just go from this one to that one. So we round it to the least number, right? So what's the least number of significant figures in that calculation? 3. This one. So we round it to this position here. That means 2.02. Now we can do 2.02 and then 0.169. Line up the decimals, subtract, and then 0.169. And I get 1.851. Right? So how do we round this one to be consistent with the rules? The least number of decimals, right? So we have to round it to that position. That's your answer. So when you have a mixture of rules, and you're not told explicitly how to do it with parentheses, then you follow this set of rules. Multiply, divide, deal with that one. Then you can do add, subtract. Okay? Okay. Let's see what we have. Let's do one more dimensional analysis. Here's a good one. So let's say we're given, lost my place. Yeah, here we go. So here's what we're given in this problem. We're given 20 mils of glycerol. I know what glycerol is. Okay. And the mass, so this is the volume, and the mass of that is 25.2 grams. What's the density? But not what's the density in those units, which would be very easy to do, right? Because the definition of density is mass divided by volume. We want the density in ounces per quart, just to be difficult. All right. So we can calculate the density here as 25.2 grams per 20.0 millimeters. Right. But we need something that'll change it into ounces and quarts. So when you have a number that has more than one unit in it, and you need to convert to a different set of units, do one unit at a time. Right. So grams corresponds to ounces, and milliliters corresponds to quarts. So we'll do one at a time. So you're given 1 ounce equals 28.4 grams, and 1 liter equals 1.06 quarts. Okay, those, you're given those. So let's do ounces first. Grams and ounces. So if you have an equivalence, you automatically have a conversion factor. You just put one over the other in whatever order you want to do the job you need. So we're going to get rid of grams, right, top, bottom, and leave us with ounces. So the grams is 28.4, and the ounces 1.00. There, there. We're left with ounces. Got that. Okay. Now, our conversion here is liters and quarts. Right? But we don't have liters. We got milliliters. Right? We need liters. So we got to get rid of milliliters. It's on the bottom here, so this has to be on top. And leave us with liters. So what's the ratio there? 1,000 milliliters in 1 liter. Right? Or 1 milliliter is 10 to the minus third liters. Either way, it works, right? Multiplying by 10 to the third is the same as dividing by 10 to the minus third. So that gets rid of milliliters and leaves us with liters. Now we can use our conversion. Liters on top, quarts on the bottom. Is that going to do what we want? Yeah. Quarts are on the bottom. So 1 liter is 1.06 quarts. Liters cancel. Leaves us with quarts, ounces. We're good. From that point on, it's just crunching numbers. Right? We followed our units of measure to be sure that our dimensional analysis is correct. From then on, you let the calculator do the rest of the work. Right? So 25.2 times 1 times 1,000 times 1. Right? So that gives us, we can do it intermediate here. So this on top would be 22.52. Well, we can keep as many as we want. 10 to the 4th. And then on the bottom, 20, 28.4, 1.06. On the bottom is 6.0208 times 10 to the second. Okay? Then we just divide those two. And I get 4.18549 times 10 to the first. Now, how many of those can I keep? Well, the beauty of dimensional analysis is it's always multiply divide. So you don't even have to use the first rule for significant figures. Just find out which one is the least. We don't have to pay attention to this one, that one, or that one, because those are exact numbers. They're conversion factors, right? Those are exact numbers. These are the only two we have to worry about. Both of them have 3, right? So our answer can have 3 significant figures. 4.19 times 10 to the first. Now, if you do one of these on a test, you don't find 4.19 times 10 to the first, what do? So, convert it to standard notation. Maybe the answer is in standard numbers. See if that was there. Okay. That's known as a chain conversion. Let's see. We better get a move on here. Physical changes versus, mixtures, homogeneous, heterogeneous, just a definition. So in order to know what a mixture is composed of, what do you need to know first? What are the pure substances? Because mixtures are always pure substances mixed together, 2 or more of them. So a pure substance could be an element, or it could be a compound that has no other compounds with it. Right? But it could be like, I don't know, my favorite, gold. Or it could be a compound like water, H2O, pure substance. You mix them together, gold and water don't mix. Right? So I guess you would call that heterogeneous. Or if you try to mix sand in water, silicon dioxide, SiO2, is predominant mineral in compound in sand. Mix that together with water, you get a heterogeneous mixture because you can watch it. Once you stop stirring, it settles out. Put salt in water, you get a homogeneous mixture, right? Up to a point. There's a point we call saturation where you can't put any more in it.
Settles out.
I'm sorry?
It like settles out. Like
Yes,
you guys want something.
right. The part that doesn't go into solution settles out. You can do that with sugar too, table sugar, but it takes a whole lot more. Right? That's how they make rock candy. You just suspend a string in a saturated solution of a hot saturated solution of sugar water, and then gradually cool it down. And the solubility decreases as the temperature decreases. So that means some of it comes out of solution, and it's attracted to that little crystal that you got on the end of that string. And as you gradually cool it down, the crystal grows bigger. You get rock candy. Of course, on an industrial scale, like they have vats of the stuff with lots of strings. Right? I guess they make rock candy still.
Yep.
You might have to go to some specialty store like Vermont Country Store probably has it. Nobody knows Vermont Country Store. My wife gets those magazines all the time. And you can go to Vermont to the home store, and they say it's a trip. It's like a Sam's Club with nothing but old-timey stuff in it. Anyway, so what's another name for a homogeneous mixture? I'm sorry? No, homogeneous mixture. It's another name for it. Solution. Right, homogeneous mixture is also called a solution. So what are some types of homogeneous mixture? Gas, gas, the air we breathe. Right? Anytime you mix two or more gases together, they always form a homogeneous mixture. Every time. Why is that? Because there's so much room between the molecules. I mean, there's plenty of room for everybody. Mix them together, they just fit right into the holes. That's not true for others, for liquids and solids and so forth. You have to make room for them. So you can have solids and solids like brass, which is copper and nickel, or liquids and liquids, like ethanol and water to make booze, or gases in liquids. You can make soda pop. That usually has to be under pressure if you want enough gas in there to make a difference. That's why when you crack the lid on a bottle of pop, it pops. It's under pressure. CO2. And of course, solubility of CO2 in the water, or in the pop, increases with decreasing temperature. So if you cool down your bottle, your 2-liter bottle of pop, before you open it, it won't pop as loud. And you'll preserve the dissolved CO2 in your liquid a lot longer. That's why I always take my 2-liter bottles and stick them in the fridge for 2 or 3 hours before I open them the first time. If you do that, you lose less of your carbonation.
So,
Not my glasses, it must be my eyeballs.
so what is propane?
I'm sorry?
Propane.
Propane?
I know it's a gas.
Yeah. Propane is a liquefied gas as we buy it from the store. And it's under pressure too to maintain its liquid state. It's a hydrocarbon. Right? 3 carbons, 8 hydrogens. That's it. Now, it doesn't have to be extremely pure, excuse me, because you're going to burn it anyway. But it needs to be pure enough so that it has consistent physical properties. But that's the primary ingredient. Kind of like gasoline in your car. It's primarily octane. Let's see. Plus some other stuff. Yeah, up to 10% ethanol. Right.
That's what attracts water to gas.
Yep. Yeah, it's bad. Yeah. You really want old-timey gasoline.
You can still buy it, but it's so expensive. It's not worth it.
Yeah. And then, of course, if you go higher than 10%, you have to have a fuel system that's designed to handle it, right? Because anything greater than 10% is corrosive on some parts of a fuel system, right? So E85s have to be special parts. It's not the engine that matters so much as the fuel system itself. It's easy to handle the burning of 85% ethanol or even 100% ethanol in an engine nowadays because they're computer controlled, right? So the primary thing that you want to avoid is knock, detonation, pre-detonation before the spark. So you control that with compression ratio and timing your spark. And I'm sorry?
Fuel to air mixture, all that stuff.
Yes. And the little computer in your car can do that, on the millisecond scale. It has sensors in there that can detect knock. When it starts to knock, it makes an adjustment. Okay. So, I don't want to run out of time. Let's see. When are we supposed to give this one up? 10:30, is it? Yeah. And then we'll go down the hall to the computer lab and do our Excel spreadsheet thing. Okay. All right, we can get into chapter 10 now. You probably want to review discussions of scientists and what they were noted for. Like Robert Boyle, Lavoisier, who's given credit for being the father of modern chemistry, before he lost his head in the French Revolution. That was tragedy. A greater tragedy, actually, was the scientist who discovered the atomic number system. That was a real tragedy. He went to World War II and died at age 28. He had already made that discovery before he went. But no more, not after that. Anyway, just know what each scientist is noted for. Let's see. Okay. No, that's not the one I want. How about the law of definite proportions, you just simply state that one. All it says is that no matter where the compound comes from, no matter what its origin, this compound comes from isolating it from the earth, purifying it from ore, or if it comes from a chemical reaction. These two compounds, we've identified them as the same. They have all the same properties, chemical and physical properties. then the other thing that we know about them is the ratio by mass of the elements in these compounds are identical, no matter where they came from. Right? So if you get, I don't know, sodium chloride, if you dig it out of the earth and purify it, or if you get it from an evaporation pond, or if you react sodium metal with chlorine gas, which is the real light show, then the product is the same ratio of sodium by mass, one sodium and one chlorine. So one sodium, a ratio would be 23, rounded off, 23 grams to 35.45 grams chlorine. But mass ratio will be the same no matter which one, because there's one of each. That's definite proportions. The law of multiple proportions we can illustrate. For instance, if you have this series, that would be have a charge, but electrons weigh so little, you can ignore the charge for our purposes here. The multiple proportion says that the ratio, if we keep the mass of sulfur constant, right, say it's equal to 1, whatever that has to be, then the ratio of these three will be 1 to 2 to 3. And that's multiple proportions. Now, when the law was devised, they didn't know that. They just knew that if you had two compounds with two elements in each one, and they were different compounds, but you knew that they only had those two elements, then the ratio would be in whole number increments, like 1 to 2 to 3, or 2 to 4, or 3 to 5, whatever it happened to be. They would be whole number ratios, multiple proportions, by mass. Right? These laws were formulated before we knew this relationship, before we could write compound names reliably. So, process of elimination. Suppose we have this one. Can we illustrate multiple proportions with that pair? No. That's carbon and that's calcium. Well, there's carbon and carbon. But there's oxygen and oxygen. You got calcium, right? So you don't have the same elements in each one. So the multiple proportions fall apart here. That doesn't work. Now, if we change it to this, yeah, that works. The ratio is 1 to 2 to 3. If this is 1, 1, 1, okay? So those are conditions of the law. It isn't until we get to atomic theory. Robert Boyle first proposed the atomic theory. Till we get to that point, then we can explain why the definite proportions and multiple proportions work. Because then we're assigning actual numbers of atoms to compounds. And those atoms have definite masses for each one. Then it makes sense. We're saying why it happens. Okay, I'm running down to the wire here. Let's see. So, if we have let's say you're given, sometimes we can write isotopes this way. What does that mean? I didn't show you that during lecture. That just means that the mass number for that bromine is 78. Right? So we could write it this way. Right? Put the 78 up there. Now, if I ask you to say, all right, how many protons, neutrons, and electrons that has? Right? Remember, periodic chart is your best friend. So bromine has how many protons? Remember, the number of protons defines the element. So bromine has 35. So we're at 35. That means it has 35 protons. How many neutrons does that isotope have?
8 times 35.
Uh-huh. 43. Okay. How many electrons does this thing have? Is it charged? No. So, how many electrons does it have to have? Same number of protons because it's neutral. Okay? Now, if it were ionized, say it was in a compound, like that, how many electrons would it have? Right. Could we get that charge by changing the protons?
Well, we can't change the protons, that's what I'm talking about.
Right. You can change the protons, but you won't have bromine in it. Right. So we get charges on atoms by changing the number of electrons. So if we add one electron, we get that extra charge right there. And that's characteristic of the halogens. If we had sodium, right, sodium would be 11. And let's say the most common isotope we said was 23. Right? So that means it would have 11 protons and 12 neutrons. And 11 electrons this way. But sodium tends to be a 1+ charge, right, when it's in an ionic compound. Right? So in order to get that imbalance, we need one extra proton. And to do that, we take away an electron. Remove an electron, there you go. Got it. An extra positive charge. Question?
Kind of, yes.
Okay.
Okay, so what I'm going to need step one is it, say, my step one periodic table, say, we go with sodium again, and we just take the mass, which is going to be 23, right?
That's the mass number.
Okay, mass number, and then the 11 protons,
Uh-huh.
and then we minus those two to find the neutrons and the protons, which is basically
Right. Uh-huh.
the electrons we take away if there's an extra positive.
If there's a charge, yeah.
Okay.
If there's no charge, then these two are equal.
And then if it's a negative charge, it goes up one.
Add one, yeah.
Okay.
If you need two negatives, add two. Right. Like for oxygen. Like oxygen is 8. Right. And the most common isotope for oxygen is 16. So that means it would have 8 protons. It would have 8 neutrons. It would have 8 electrons. But when oxygen is in an ionic compound, it's usually a 2- charge, right? -1, -2. Right? 0, -1, -2, -3. So in order to get a 2- charge, we have to add 2 electrons. There you go. And that gives you your 2- ion. Okay. Let's see. memorize those symbols. We won't go over that. How about, and we've gone over naming compounds, right? So that convention should be firmly in hand. How about this one? We'll fill in a table using what we just learned from all of that. So let's see, our table has some symbol down here, number of protons here, number of neutrons down here, number of electrons here, and net charge down here. Okay. Let's see, 1, 2, 3, 4. I need 4 rows. Okay. Go. Now, given information. All right. Let me use one color for given. And we use the other color for answers. So this is given information. 206 B. And this one has 31 here, 38 there, 3 plus here. This one has 52, 75, 4. This one has Mn plus. We did that one earlier, that's lead. How about this one? Manganese, right? Anybody remember Caddyshack, the movie? You remember when Chevy Chase and Bill Murray are talking in his digs? He's going through the book and he says, I'm going to be head greenskeeper in 3 years. So he says, people don't know that's chinch bugs. Manganese. Remember that? He was talking about manganese. Right? Manganese in popular culture. 30 and 2 plus. Okay. Let's see if I got all the givens. 3. Okay. So now we're going to fill in the chart for all that other information. Okay, let's start with lead. What do we know about the number of protons for lead? 82, right? 82. Is there any charge on that lead? Nope, no charge given. So we can say the number of electrons is also 82. And we can say the charge is 0. Okay. How about neutrons? How many neutrons do we have? 124. See if that adds up. 6. Yep. That one's done. How about this one? Can we put in a symbol here? 31, right? 31. Gallium. Gallium's an interesting metal. Its melting point is 32 or 34 degrees centigrade. What's body temperature? 37. So you put a chunk of gallium in your hand and it melts. Okay, what else can we do? Well, we can also put this one up here. Right? Using this as an example. You don't necessarily have to, but let's do it anyway. So 69 there for the mass number. How many electrons? There's no charge, right? Oh, there is a charge. Almost missed that one. So we need the charge, Now how many electrons?
28.
Right. We have to take away 3 electrons to give us an extra 3 positive charges. There we go. How about this one? 52 protons. Tellurium. I don't think I had you memorize that one, did I? But you know the symbol, right? You can find the symbol from this. Right. How about mass number? 127. Right. Protons and neutrons. How about charge? We got how many extra electrons? 2. So that's 2 minus. Okay. Manganese, 2 plus. Okay, this was given, that was given. All right, so manganese, it's over here. 25 protons. So the number of, well, let's see, mass number would be 55, right? And the number of electrons, we have to lose 2 to get a 2 plus, right? We got to lose 2 electrons, that means 23. There we go. So with that given information, we had everything we needed, well, plus our periodic table. And you'll always have the periodic table. You're never deprived of that. Okay. Let's see. How about let's name some things here. Let's take compounds and see if we can name them. We'll write the compounds. How about this one? Suspect polyatomic. If you have 3 and one of them is oxygen. So if you suspect polyatomic, you're right. This one acts like a single unit. So you look in your chart, the polyatomic list, and you find out that this one is sulfate. So we have iron, sulfate, but where does iron come from? It's a transition metal. So another suspicion probably has more than one positive charge. Well, if we look at the formula, right, 2 minus, you can find that from your polyatomic, 2 minus is the charge on sulfate. So since there's only one of these for one of those, that means this one has to be positive charge. So that's the name for that compound. How about that? Again, suspect polyatomic. So you look up your polyatomics and you find this one is acetate. And this one is, Na is sodium. Can sodium have more than one charge? Nope. It's stuck. One charge. Plus, this tells you what the charge is because this polyatomic, the charge is defined by the polyatomic. It's a -1. This one has to be a +1. And then you see on the table where it comes from. So that's type 1 compound. How about, how about this one? Suspect polyatomic. All right, you got 3 elements, and one of them is oxygen. But another giveaway is parentheses. That parentheses says this acts as a single unit. That's the hydroxide ion with calcium.
Calcium.
Right. And hydroxide is always -1, so that means calcium is +2. But calcium is always +2. Right? It comes from the alkaline earths. So we only have to say calcium hydroxide. Yeah, let's do this one. How about this one? Polyatomic again, right? We're throwing a bunch of polyatomics at you. That's a carbonate. So you look up the carbonate, and you find it has a 2- charge. Right? That's important because you've got one of these and one of those. This one has to be 2+. So now, and nickel comes from over here somewhere. Where is it? Yeah, there it is. So that's nickel 2 carbonate. Okay. Let's see. Okay, let's go the other direction. Let's give you the name and see if we can write the compound. See if I can write the compound. With your help. Well, let's say, let's get that. How about this one? Aluminum oxide. Okay, we know we have aluminum, and we know we have oxygen. But how many of each? Well, oxygen is always 2-, right? How about aluminum? It's always 3+. Okay? It's one of those that's fixed, type 1. So the best way to do this with a charge here, 2-, 3+, is cross. So this one becomes 2, this one becomes 3. And you check yourself, right? If this is a 2- and this is a 3+ charge, right? 3 times 2- is 6-, 2 times 3+ is 6+. And they cancel. Okay? Sometimes we call it cross and multiply. But you don't have to write the charge for the compound. You just write it like that. Oh, let me do this one. Ammonium ion. The polyatomic, right? You're not going to find ammonium anywhere up here. So you can assume it's polyatomic. Look it up. In fact, ammonium is the only positive polyatomic ion in that table. It's got nitrogen, 4 hydrogens, and +1 charge. That's ammonium. That's the only positive one you need to know. The rest of them are all negatives. So where do we know ammonium from? I'm sorry? Ammonia in the bottle, in the cleaner.
Yeah, what is it?
That would be NH3 without the charge. That's ammonia. You just bubble it through water and you get ammonia. But this one we find in compounds. Right? One compound that is commonly in is combined with nitrate, ammonium nitrate. Right? All you have to do is add 6% fuel oil to ammonium nitrate. You know, put a piece of dynamite or a plastic cap in there with it, you get a big bang. That's how they dropped the Alfred P. Moore building in Oklahoma City. It's with ammonium nitrate improvised explosive device. That's why ammonium nitrate in large quantities is strictly controlled by the federal government. You basically either have to have a special permit, say you're a manufacturer that you need it for, or you're a farmer, and you can get it. But it is actually cheaper as a nitrogen source, right? Everybody? No, you don't look at bags. We already determined that. You look at a fertilizer bag, you see 3 big numbers on it. Or a bottle that you buy in the garden store. This is the common one. 10, 10, 10. Sometimes it's blue, might have a color added to it. This means 10% nitrogen, 10% phosphorus, actually it's P2O5, and 10% potassium, that's K2O. So these are the 3 main ingredients in fertilizer. They're the macronutrients, they say. Nitrogen, phosphorus, potassium. And this nitrogen is probably ammonium nitrate, but it could be some other form of nitrogen, like sodium nitrate or potassium nitrate. Particularly if you want extra potassium in here for that, then you get both of them with one compound. But as a nitrogen fertilizer, if you're on a large scale farming, then you have 2 other options that are relatively cheap. Well, one of them, you need special equipment. You can use this one as a liquid, pure anhydrous ammonia. You have to have stainless steel equipment to handle that. And you have to have, when you use it, you fertilize your crop, it has to be injected into the ground, right? Because as soon as the pressure is off, it turns to a gas. So you want it in the ground where it can react with the water and stay there. Otherwise, you paid all that money for your nitrogen, it's gone. But that one, you can inject that into the ground. Or another one that's a little easier to handle is urea. CH3 taken twice with oxygen. Nope. Urea. So in that compound, talking about nitrogen, I don't have any nitrogen in my molecule. Okay, that's urea. It's the same urea that's found in urine, right? But if we concentrate it and put it in a little white frill so you can handle it and throw it out on your field, then it serves fairly well as your nitrogen source. And you get 40%, 46% nitrogen. That's extremely high. It's a good concentrated source of nitrogen. The highest you can get out of ammonium nitrate is 32%.
I know some poultry manure acids that are a little bit before you put them for
Yes, right. So the poultry produces nitrogen in the form of uric acid. Okay, and whereas each molecule of ammonia has 1 nitrogen, each molecule of urea has 2 nitrogens, right? Because this external 2 applies to everything inside, so there are 2 nitrogens there. The nitrogens in uric acid, I think there are 4. I think there are 4 nitrogens in uric acid, and I'm scratching my head for the formula. You know, I have to defer on that one. But it's a more concentrated source. But it also has a higher, what they call salt index. That is, as it decomposes, it produces positive, negative ions that increase the concentration of the ions in solution, and at a certain point, they're injurious to your plant. So if you compost it, you give it time for that uric acid to decompose into urea and ammonia compounds. And some of them even organic, because you've got a lot of microbial activity in there, bacteria and fungi. And they convert it to less harmful versions of nitrogen. Then you can put it on your garden and you're okay. We used to collect cow chips on a flatbed trailer where I had my garden. My boss had, how many was it? Like 60 head of cattle. So we go out with a flatbed truck and just pick up cow chips and throw them on there. Then we take them back to our garden and dump them in a pile and let them get rained on for a couple of weeks. And in Louisiana, it doesn't take but a couple of weeks to get rained on pretty good. But what that would do was, it had nothing to do, well, it had something to do with nitrogen, but not as much as with the actual salt content of the feces. Right? Because for their health, he would put out salt blocks. They ingest that salt, and then some of it would come out in the urine, some of it would go right on through in the cow pies. So we would let it leach the salt out of them. Then we could put them out in the garden. Right, so that salt index can be a plant killer. That's why you don't want to use too much wood ash either. Right. Wood ash is good for potassium, primarily. Right, so if you're low on potassium, then it's a good source. But other than that, you've got to supply the other two. Anyway, about out of time. Let me see what else needs to be covered before. Oh, we were going to do, well, we did one anyway. You need to practice. Well, 50 ways to name your compound will give you some good practice with converting from one to the other backwards. Compounds to names and names to compounds. So that's a good place to go. Let's see. That pretty much covers it. For a review, we'll take a look at this review document right in Blackboard. You'll probably recognize some of the things we did here in that document. Skip over those. But the one thing about my review documents is there's lots of redundancy. You do the same type of problems, they might be worded a little different, just to see if you're on track with the theme. And we'll meet up in 146. Everybody know where 146 is? Know where my office is? Right. Go just past my office and take a left, like you're going to the rotunda. Second door on the left, and that's the computer lab we're going to be using. We've got time for a break, if you need a bathroom break on the way. Do you guys want your stuff back, or are you happy with it?
Yeah, I want to take my break.
Okay. There you go. Oh, it's in my office. We'll go by my office and pick one up. Let me stop this so it can be converting in the meeting.
I'm sorry.